Okay. First, let me say it's a privilege to be here. Part of my travel getting here involved half a day on Texas highway in the sun without water. So it's nice to live in a society in a nation that lets us do science and does have science conferences. And so with that, I want to talk to you about the role that physics plays in gene expression. It's going to be fairly conceptual in nature. I'm not going to give a lot of technical details or theoretical work experimental. And it's mostly going to be about explaining some really general properties of gene expression, particularly transcription, that I've been obsessed with over the last year. And to understand what I've been obsessed with, I want to take a look real fast at what modern day gene expression experiments look like. So put a fluorescent probe into DNA, and as it's transcribed, it fluoresces, and from the fluorescence you can infer the copy number of an RNA in a particular cell. So this is like the time trace of one cell. You can also look at many cells and make histograms of the RNA levels in all of those cells. And as people have gotten better and better at this, and studying many more genes and many more organisms, some really interesting properties about transcription in general have sort of emerged. So this is from a science review paper a couple years ago, and John earlier talked about the phenofactors, so that's what's plotted along here, versus the log mean RNA levels. So what's interesting, most obviously, is that somehow yeast is able to transcribe just much more than E. coli or animal cells are. And then also there's this high mean, high variance relationship that's seeming to emerge in E. coli animal cells, but isn't present in yeast cells. So to understand that, I'm going to try to convince you that the helical nature of DNA is really crucial to understanding where that limit and that property comes from. So first you have to imagine that DNA exists in some sort of topological blocked organization, so that it's constrained ahead of and behind the polymerase, and I'm not going to spend much time talking about it, but this is generally true in bacteria and eukaryotic cells, but it's not really true in yeast. And second, you have to imagine that when transcription occurs, the polymerase and the nascent RNA chain has to rotate around the DNA as the gene is transcribed. And as this happens and the RNA chain gets larger and larger, it starts to twist the DNA. And also, as it twists and becomes heavier and heavier, it also starts to drag the DNA through the polymerase complex itself. And so multiple twisting mechanical processes happen, and the strain is put onto the DNA. This is the basic idea behind what people call the twin domain idea of transcription, where ahead of an RNA polymerase complex, the stress is increased and you get positive supercoiling, and behind the RNA polymerase complex, the strain is decreased and you get negative supercoiling. And what I'd really like to propose is for us to think about what a gene looks like if it's regulated only by physics. So earlier when we were talking about all these other things, promoter binding, the concentrations of promoters, just forget about that. Imagine that a cell is desperate, it's gung-ho, it's going to transcribe whatever gene as much as it can. What stops it? So obviously, the rate of production is the most obvious thing, and that's more or less controlled by the velocity of the polymerase complex. It can only go so fast, so it can only make so much, and it dies or it gets translated, and that's more or less what controls the level of a particular RNA inside of a cell. But if you combine it with this twin domain idea of transcription, you have to also think about how the mechanical strain that the polymerase complex puts onto the DNA is relieved. So the cell has these things called topoisomerases that take away the mechanical stress that is put into the DNA molecule by the polymerase. And what I'm going to tell you is that a gene that's regulated purely by physics is the dynamic process of strain getting put onto the DNA and strain getting taken off the DNA through the polymerase and the topoisomerase. And we're going to be really interested in the type 2 topoisomerases, which are the ones that are primarily responsible for taking away the increased tension in front of the polymerase complex. To convince you that this is actually happening with two relatively recent experiments. The first one on the left is a pure physics experiment where one end of a DNA molecule is attached to a magnetic and optical bead that they can observe the torque and the tension and the rotation and control it as a polymerase complex moves along the DNA. And it's attached to a glass slide so that you can see how it goes along. And what's really interesting is that, my pointer is pretty faint, but it stalls. So it can only operate up to some critical level of torque. And once it reaches that, it pauses and doesn't move anymore, so transcription stops. In fluorescence imaging experiments, where they watch transcription happen and can selectively remove or put in those elements that I told you about that take away the mechanical strain that's put onto the DNA by the polymerase complex, they see that the positive supercoiling arrests the transcription, and it can't restart again until they add the gyrase back. So what I'd like to say is that the physically regulated gene has this mechanically induced silence, and it takes gyrase to come back and relieve the induced torque and stress for transcription to happen. So this is sort of getting back to what people have known for now. For a while, is the burst into those periods of activity and periods of silence. And what I'm going to tell you is that for really, really widely transcribed genes, it's the physical mechanical feedback and interplay between the gyrase and the polymerase that causes this burst. So most generally, we're going to think about four different states. There's two states where the gyrase is bound, and there's these two, and then there's two states where the gyrase is unbound, and then also there's two states where there's no expression, and two states where there are. And so what we're going to really think about is fixing the gyrase binding and unbinding, and the unwinding rate is actually very fast, so we're going to more or less forget about that for now, and we're going to try to understand this process of the gyrase falling off, which happens on a relatively slow time scale, the self-arresting of the polymerase, and then the reactivation of expression through the rebinding of the gyrase. And I'd like to understand how varying levels of this arrest rate change the behavior. So these curves are R over lambda parameterized. So again, this is log space, so really these exponential curves are linear, and if this was plotted on a linear scale, but to make it obvious with experiments, we'll keep it on the log scale. So this plot is our R over lambda curves for varying values of A and fixed gyrase concentration. So T on and T off fixed. These curves are more or less the opposite, where I've fixed the arrest rate and I'm changing the relative strength of the binding. And what's really interesting is that it's more or less going to provide a lower bound to how fast transcription can occur. So don't get too upset, but I'm going to just say that all the biological activities, so promoters, et cetera, happen in what was previously just this two-state sort of setup where there's some silent state and some active state. So when you put that back on top of it, what you see is that you can regenerate all sorts of, you can re-explore the whole phase space of the mean versus fatal factor relationship. All right. But this green curve is the arrangement where K plus is much, much larger than K minus. So again, that's the state where the cell is doing all they can to turn the gene on, and even through all of its struggle and effort, it comes up against this wall. So this is the mechanically induced silence of the physically regulated gene provides a lower bound to the cell's ability to transcribe. Going back to the first slide, like I said, I didn't really give you any citations, but it's generally considered that yeast chromosome DNA is not arranged in a way that there would be barriers to transcription. So physics doesn't play a role. It can transcribe at really, really high rates. There's no boundary. Whereas E. coli, they exist in these topological domains, and you see there's a really strong boundary to how much RNA a yeast can make for any gene. And I think it's more or less because of this physical process of mechanical force being put onto the DNA and the gyrase sometimes not being around to take it away. So I would say that's just the first signature of physics in gene expression. The second one, and I'm going to be more or less on time, is in the wait time distributions between the bursting between an on state and an off state. Again, in this fully induced, physically regulated gene setup, we go back to what I wrote down originally. The wait time distribution between being on and off, so the time that the cell spends transcribing versus off, are determined by these rates. So if the gene never gets turned off, A goes to 0, and you get back to this Fano factor equal to 1, but when this A exists, and you enter the silenced state, so the off state, you get the lower bound that I was talking about, and that's present in the wait time distribution. So, and then also, to get turned back on, you have to have two processes happen. You have to both have the gyrase bind, and then the gyrase has to work, and you get this peaked distribution. And with that, I'd like to summarize and say that I think it's very obvious that physics plays a role in gene expression at a very, very broad, abstract level. I would also like to say that it's interesting because many targets of antibacterial agents and cancer therapies target the regulation of topoisomerases, and also say that obviously there's more work to be done.
Thank you, Stuart. So we have time for questions. Go back there first.
This is nifty, thanks. I'm here. One question, do I get your model right that you basically sort of assume it's either strained or not strained? I mean, in principle it's torque, and so it's a continuous,
so
it could be sort of, there will be a continuous relationship between speed and torque, but...
that's part of the nuances and the details, and so there is slowing down when you get close to the critical torque, but yeah, in what I've shown, it's very much true that I'm just saying it's going at a constant rate up until the critical torque, and it stops, and that's more or less true. There is slowing down, but it's not.
No, it's definitely a good approximate.
Is it true that according to your hypothesis, if you overexpress gyrase, you would expect Fano factor to increase?
I think it should decrease. Because if there's more gyrase present, then the rebinding happens very, very fast, so there's very, very little time that the gyrase isn't attached to the DNA.
So has anybody actually ever done that?
So a part of some of the experiments I did, I showed these ones down here. That's part of what they did, is they changed the gyrase concentration, and they saw that.
Oh, I meant in the living cell.
They did some, I'm not sure how living the living cell was, but they did it more than more or less living. I don't know, I'm not an experimentalist, so.
Okay, one more question here.
Very, very nice. So, do you think the gyrase is unregulated and just sitting there sensing strain and popping in when necessary, or do you think it's regulated such that even if there is strain, it doesn't come in to relieve the strain in a kind of a gene regulation framework. So what do you think, regulated or unregulated?
There's certainly aspects of both. So there's lots of genes that are correlated with the expression of the proteins that make the gyrase, and so in that sense it's regulated. As far as the precise action of the gyrase itself, like does it see I'm not sure. So
does it see tension? Does it see torque?
That I'm not sure about. I do know that it becomes less effective with especially higher tension because of the mechanism of the relieving of the torque. It has to wrap the DNA around itself. So if it's really, really taut, it more or less can't even operate. So it's possible you could enter some state where the gyrase can do its job.
Great, thanks.